So hi, in this video we will talk about the V curves in synchronous machines. So let's have a look at the situation with a standalone operation. So okay, in this one we have a single generator, right? So it's not connected to a load grid or anything like that, but it is just connected to a three-phase load. So you can think that one like, I don't know, a diesel engine, okay, diesel motor, okay, so connect to the generator and you are supplying some load. And of course we have here the field current, okay, and normally there's a closed loop controller, automatic voltage regulator for that field current. But first let's look at what will happen if we just keep the field constant. Okay, so we will keep IF, the field current, constant, but the armature current, the load, keeps increasing. Okay, so again it can be in like different power factor conditions. Let's see at like unity power factor first. So if the field current is constant, okay, so I mean different from the grid connected synchronous machines. So in the grid connected synchronous machines I can just draw the VT and that will be like a constant magnitude, right? The VT will not change in a grid connected system, but not in a standalone operation like that one, because there's nothing that holds the VT constant as in like in parallel connected machines. So here what I can do, I mean this is my EF and the magnitude of EF will be constant if the field current is constant. So that means I can only move EF along that circle. So I remember it was the circle diagram as we discussed in the previous week. Okay, so here again, if EF is like that and if the current, okay, if the current IA will be like that, so you have a power factor. So again VT now, you know, is defined by the mechanical load or the electrical load. So the load angle and the magnitude is field angle is constant. So you cannot say the magnitude of IF will stay like that, but what you can say, you should go from the inverse. So if EF is here and if IA is that much, then my JXSIA will be here. Okay, so if XSIA is here, so that means my first like terminal voltage, let's call that VT1, will be here. Okay, so what happens if I increase the load? If I increase the load, then that definitely means the load angle is going to increase, because increasing load means increasing torque, and you can increase the torque by increasing load angle. So EF will move from here to, I don't know, somewhere here, right? So the load angle now has increased, right? And actually you can see like now if it is still working in the unity power factor, so that XSIA is increased from here to there. Okay, so JXSIA magnitude wise, you know, that is increased. So again, in that case, our new VT will be something like that. So that is, you know, the load regulation. If you just let me draw it here, right? So let's say this is magnitude wise, this is our VT magnitude, and let's say this is our armature current. Okay, so again it is similar to a transformer. Remember, in a transformer Actually, transformer can be modeled as a series reactance. You have one input AC, output AC. So you can still look at the transformer model from the previous semester, and you can think it is like a synchronous generator electrical wise. So what was happening in a transformer, as we increase the load, the output voltage was reducing. So here we have the same relation as the loads increase. So you can see VT will start from, let's say, no load condition, and if it is at no load, if there is no current, there will be no drop, so that will be equal to EF starting from here. And as you increase it, try to plot it here, so you will have that kind of graphic, right? And you can think the same way with the lagging power factor, right? So if you have the EF like that, so EF only can move along that circle, and in this case you will have the JXS here, and as the load is increased, okay, so that will move in counterclockwise direction, increase the load angle, and therefore our JXS component will go like that, and you will have less and less voltage. Actually my drawing is not accurate, but actually if you do for the same values, you will see you will have a larger voltage drop with the lagging power factor. Okay, so lagging power factor will be here. However, if you do the same thing for a leading power factor, okay, so if it is like that, theta IA, so now our EF, let's say, is going to be somewhere here. It's that curve, so it's going to be moving along that line, right? So if you increase the load, if the load angle gets larger, and if that one gets, let me redraw again, and relate that accurate. Let me draw the VT larger. Okay, or let me draw EF somewhere here at first, and this is our IA, right? So if I increase my power factor, if I increase my load the same way, then you will have that much, and then your IA will be larger here. So this is JXS IA, again this is JXS IA. So now you can see it was here at first, but now it gets larger, right? It gets bigger. So the terminal voltage as the load with the leading power factor is something like that. So leading power factor. So this is, of course, if field current is constant, but of course, we don't want that kind of operation normally. What we want is, like, we have the automatic voltage regulator AVR, and AVR compensate for that voltage drop by increasing or decreasing the field current. Okay, so that is actually we already drove that graphic. So it can be, you cannot, in this case you cannot or you shouldn't keep the field current constant. However, you need to be adjusting that one. So now let's have a look at from previous information. Let's try to draw what will happen. what will happen to the field current with load if I want to keep the terminal voltage constant. So let me write that one to be IF field current, and this is IA load or armature current. Okay, so again, if you look at what will happen with IF constant with the lagging power factor, as the load increases, I have the largest reduction in EF. So somehow I need to compensate for that. So that means I need to increase IF as the load increases for lagging power factor. Okay, then for unity power factor, yes, it is reducing, but somehow, you know, it is less than lagging power factor. So that means the compensation for the field current is going to be less for the unity power factor. And for the leading power factor, actually the VT terminal volts gets larger and larger as I increase the load. So I need to reduce the field current. As the load increases. So, of course, you don't have to define those things mathematically. What's happening is you have a voltage sensor, there's a feedback loop, there's a controller, P controller or PI controller, and actually it compensates for that automatically using the AVR. Okay, so now let's look at the case for the synchronous generator. So in a synchronous generator connected to infinite bus, so that means our grid case is slightly different. Why? Because in that case here there was nothing controlling the magnitude of VT terminal voltage, so it was all going up and down. But in a grid connected machine, so the voltage is same regardless of either you are working as a motor generator or the amount of current. So it is quite a ideal voltage source. And again, you cannot change the frequency. You can either supply some power, consume some power, but you will not have any effect on the frequency and voltage of the generator itself. So in our equation, it is again the same equation, but in this time, like VT, that one is constant. You have no control over it. That is there. So that means the relation between EF and VT determines the amount of current. So you can again calculate if the machine is going to operate in motoring mode or in generating mode, or if it is going to work in leading or lagging mode, is directly calculated by using the relation between EF and VT, because that one is constant and that one can be controlled by IF. So by changing IF, you can actually control how much current is going to flow or what will be the power factor of that current. So in grid connected synchronous machines, there are two main operation modes. One of them is the constant excitation. We talk about that one in the constant excitation, and actually you can click on the same animations here. So let me try to draw those things again. So this is our VT, and its magnitude, its position, that is fixed, so that doesn't move, different from the standalone generation. And that is our EF, that one. Okay, that is our EF. And if it is working at constant excitation mode, so that means its magnitude, let me draw it here. So its magnitude is going to be constant, so it will only move along that circle diagram. It will move up and down here. So this is the constant excitation. Or in the constant power mode, again the Vt, that one is fixed, that Vt, that is fixed. So now the magnitude is not constant, but the power is constant. So for example, if you have a hydroelectric power plant, that means the power, the real power, the mechanical power coming to the hydroelectric power plant is constant. So that means that will only move along that circular direction. Why? Because EF times sine delta is constant. So this is the constant power operation. Right? So either you can move along the constant power, or you can move along that circle with the circle diagram. So actually that is what we already derived. So EF sine delta is equal to XS IA cos theta, and if it is at constant power, that term is constant, which makes EF sine delta constant. So now let's try to draw another thing. So let's try to draw IF versus IA if the power is kept constant. So I'm going to draw here, and again you can calculate, that will be J XS IA. So what will happen if I move it along that curve? What will happen to XS IA? So if let me draw it here. So let me just give me a second. So we have Vt here, okay, that is constant and we cannot move that one, and that is our EF at first. Let's say it is at unit power factor here, okay. So at that part, this is J XS IA, that is EF. Sorry. So EF magnitude is proportional with IF. So I would like to draw what happens to IA. So, and the magnitude of course you can see it from here, XS IA magnitude obviously is proportional with IA magnitude. XS is constant. So you have here operating at unity power factor, and the magnitude of EF will be that much. So what happens if let me draw the diagram first. Oh. Come on. Okay, sorry. Let me try to draw the coordinate system. So what I would like to draw is IA armature current versus IF. So this is field current. So this is the armature current. So here I am getting some EF, or I am getting some magnitude of EF for that value. Okay, so for that value, let's say I'm operating some value here and some current here. So that is our initial point. So then I decide to increase IF. Remember that one is working at constant power mode, so the green vector EF can only move in the horizontal axis, right? So in that one, so if I increase IF, then I will have that one. Let me define that one as EF1. So this is EF0. So this is at first IF0. So this is IA0. So now I move somewhere here. I increased IF. So as a result, my vector or JXS vector or similarly IA vector will be increased. Like now it is large. So I increased IF and that result in increased IA. So it is somewhere here. So this is IA1 EF1. Okay, so for IF1, this is IA1. Then I say, okay, so let's see if it will go like that or in other direction. So for that, I reduce my field current. I give some current like that. So then the magnitude of EF will get like really small. So it will come somewhere here, right? So let's call that vector EF2, and this one is IF2, right? So in that one, actually, let's have a look at the current magnitude. So this vector is that vector is IA2, not directly, but it's proportional. So again, that was the minimum value. It was increased here and it was also increased there. So somehow we ended up having, maybe not, it doesn't have to be the same magnitude, but it is somewhere like that. So actually, if you just draw all those lines together, okay, so you will have that kind of vector. And let's have a look at what will happen if I increase IF. If IF is increased, so that means my current is like that. In order to have that current like that, then what should be my current for IA1? So it will be vertical with that value. So this will be IA1, and at the minimum point is set the unity power factor. And in order to do that, you need to have a leading power factor. So that side, okay, you can see from here. So that side is lagging power factor and that side is leading. So suddenly you have some control over the power factor using the field current. Okay, if IF is the same, let me write like field current increases, then it becomes lagging. Okay, if field current gets minimum, then it becomes leading. So that is actually, you can control the power factor of a synchronous generator by controlling the magnitude of the field current, and those ones actually called the V curves of synchronous generator, and this is for one power level. If you just do it for different power levels, you will have different V curves. And actually this is maybe a better this is the same plot I do with different currents, and actually you can see how it changes the power factor, how it changes with the magnitude and excitation. Anyway, so if you draw all those things together, what you will find is you will have for the same power, I mean this is for same power, this one is, again let me write here, so that side is lagging power factor and the left hand side is a leading power factor, right? And as you go up, as you go up, that is actually increasing power. Okay, this is armature current. So if we are just working at the no power, so here, so this is no power. No power means like no real power, but you can still, at no power, you can still generate some leading or lagging power factor. So these are called, V curves, and you can see that kind of graphs in datasheets of synchronous machines. So let's have a look at for the motoring mode. Okay, so here you see the same graph, and as it is still working in the same constant power operation, so it is only moving along that circle. So again, if you are working at that position, let's say unity power factor, then you have the minimum EA. But the different thing is, let's have a look at what will happen if it is working with the lagging power factor. If it is working at the lagging power factor IA1, so that will result in a vector like that. So you need to have a small EA magnitude. However, as you go to the leading power factor, your EF gets larger and larger. So that is why, like, we have like inverse relation. Again, you can refer back to our previous video for the flow of reactive and real power diagrams. But if you actually draw it for the motoring mode, it is exactly the same thing, but the difference is the larger field current gives you leading power factor. Okay, so in the generating mode, larger field currents gives us lagging power factor, but if it is working as a motor, then it is leading power factor, like working it over excited. Or if it is working at the lagging power factor, so that results in smaller IF current. So they are, just replaced, that regions are replaced between motor and generator. So in motoring mode, large field current makes the power factor leading. Okay, so again, there are a couple of useful animations that you can try yourself and see different conditions. So that brings us to synchronous condensers. And again, like controlling power factor using the field current is kind of useful in power grid or in some other applications. So the idea is, I can connect a motor and I can operate it at no load. It is not connected to anywhere, and by using that motor, or I don't know, in a factory, maybe you already have the synchronous motors and that kind of thing. So in power grid, they just give you some penalties if your power factor is too low, if it is leading or lagging. So you need to have, maybe you did your summer practices in a factory like that. There are some compensation systems. Mostly they are capacitors, so you can control the amount of parallel connected capacitors in a system to make the power factor closer to unity. Okay, so you can do it using capacitors, or you can use it synchronous motors work as a capacitor. So if you just increase the field current, they will work in leading power factor, so they will have the same effect as connecting capacitors in parallel with other equipment. Or I don't know, maybe your other equipments in the factory are lagging or leading, so you need to compensate for that one, so you can reduce the field current for that kind of compensation. And these are called the synchronous condensers. So they are either used to deliver or absorb reactive power by controlling field current. So you can make it operate as an inductor or operate as a capacitor, which is kind of useful. And actually they are kind of useful also for the power grid of a country. I think in Brazil they have, you know, that kind of equipments, so it is like really similar to a motor. It's a really large motor, but what is the difference? The difference is you don't have any load connected. The shaft is just enclosed. So I think just to, you know, minimize friction and any outside effects. So it's just closed here, it's closed here, but there's some mass actually rotating inside. So by just controlling some field current, maybe just a small amount of current, you can actually compensate for all power factor fluctuations of the grid. Okay, so again, this is another one, I think, from Brazil. So it is like 100 megavolt ampere reactance. So it is not a motor, so it is not rated with the watts real power, but it is being used by the Brazil grid to control the power factor of the grid of the Brazil. Okay, I mean, for curious students, I strongly advise you to have a look at those reading materials, and also you can have a look at the manufacturing video. That's quite interesting. So then let's talk about up to now. We all talk about the ideal case, so we didn't include any resistive components or anything like that. But in reality, there are some losses in all system, and you know, our power flow, if it is working as a generator, it starts with actual applied torque times the rotational, you know, mechanical speed. So it's rotating. It can be, I don't know, hydroelectric power plant. So that is the power equal to, you know, amount of power produced by the water heating to the turbines. But on top of that, you can have some friction and windage losses, or you can have some core losses. You can have other, you know, straight losses with the enclosure or that kind of things. So actually we don't model those things in our equivalent circuit model. In the equivalent circuit model, you know, all that friction, windage losses are excluded, so you can model them in a mechanical system, and probably you will do that in your homework assignments and also in your experiments. Then once you exclude those things, then you come into the actual, you know, torque getting into the surface of the rotor. So that is the now torque that is being converted to electrical energy. Then on top of that, we have I square R losses. I mean, again, large synchronous machines are quite efficient, well over 95% efficiency, or even larger ones has 99% efficiency. But we have two main copper losses. So one of them is the I square armature current times armature resistance, and don't forget to multiply it by 3. Okay, so this is the stator losses, let me call it. And on top of that, I mean, these are for copper losses, we have the field current resistance times the field current, field winding current squared times the field winding resistance. And again, you know, that one is really small compared to the armature losses, but you know, there are two other systems, and we don't have any tree here because it is excited by DC. So it is just a single field winding. So it is not a three-phase system, but the rotor is excited by DC. And apart from that, then you have the output power. Again, if you are taking line-to-line voltage, it is square root 3 times VL IL cos theta, or it is 3 V phase I phase times cos theta. They are the same thing. Okay, so I mean, if you have some kind of synchronous machines, so what are the operating limits? So for example, if it is like written 100 kilowatts on the motor, can I run it like 200 kilowatts, or why not? You know, let's have a look at those operating limits. So first of all, we have the the limiting factors of a synchronous generator can be the stator heating. So it is proportional to armature current. Remember, the power losses are IA, or let me write, it is 3-phase IA square times RA. So if the heating system, the cooling system is not enough, then if you just draw more and more current, then that will generate more and more heat inside the machine, but it will not get rid of that excess heat. Then the temperature will go up and up. Then at some point you will damage the insulations of the windings or any other damages. So first of all, the stator current limits the heating or the operating temperature. And the second one is the rotor heating. Maybe your the stator current is well within the limits, but you are giving more and more field current. Then at some point you are generating some IF square times RF. So then that will create some rotor heating. And on top of that, even if it is not heated, the magnetic core can get saturated. Okay, it doesn't have to be like thermally limited, but it can be magnetically limited due to saturation. Other thing can be limited by the mechanical power input. So I don't know, if it is a diesel engine, maybe the size of the diesel engine is limited, or if it is a natural gas power plant, the amount of steam that can be generated using the natural gas furnaces is limited. If it's a nuclear power plant, then the number of nuclear, what are those called, rods, are limited. So there is a kind of safe limit for the amount of steam that you can generate. So there's again some mechanical power limit. Okay, and on top of that, you don't want your system to get unstable. So unstable means, so remember the field current, so torque was something like that, right? So this was load angle, so this was 90 degrees. So you are generating some Tmax. So you want to operate, within that area, because if you somehow go above that point, then you will not generate any more torque. Actually, I wish you were doing your experiments. If you do that in a synchronous machine, and if you increase load, and if you lose synchronism by increasing that torque, and that torque is also called the pull-out torque. So that is the maximum torque that you can give, and if you are exceeding that king by the mechanical or electrical load, then your machine loses synchronism and quickly stops. If it is grid connected, then it will just do crazy things like losing synchronism and gaining it again. Or if it is some damper windings, then they will create some extra torque. Anyway, so that is the theoretical limit, but in reality, actually, you don't want to push your machine that much. So probably there is a safer region that is defined, so you don't want to go over through that pink area. Okay, so it is usually less than 90 degrees, but theoretically the load angle should always be between less than 90 degrees. So if you put all those together, so we have that kind of graphs. Actually, it seems kind of complicated, so let's go one by one. So one of them is the prime mover limit. So this is our power limit. Remember, the power, in constant power we were moving in horizontal position. So if you go above that point, that means you are generating, you are going above the mechanical power input limit. So you don't want to go over that one. So that region is is off. So you shouldn't be going above that one. And the second one, or sorry, not the second one, but the rotor heating one, IF is limited, so there's a limit to the maximum EF. So the size wise, so this is our origin, so EF, you know, it's not drawn here, but EF can move somewhere here, so that will be along here, so that is rotor heating, so limited by EF magnitude, so therefore IF magnitude, so rotor heating or saturation limit. So again, you shouldn't go beyond that position, right? And for that one, this is your load angle, so you don't want to go technically, again it is, you know, 90 degrees, load angle is here, but you want to put a limit, so there's a safe area, so that is the stability limit, so that one ensures like lambda is less than 90 degrees. Okay, so you have, you know, those limits, so we have stator, you know, power limit and other ones, so you can actually operate across that region. And again, this is like written in terms of the watts, wars, and, you know, real power limits, so that's it's not really important for this course, but the important thing is now we have some boundaries and we can safely operate inside those limits. So in a practical application, what you see is something like that. So let's have a look at that value. So again, this is some real generator data, and actually in a practical hydroelectric power plant or thermal power plant, you know, they always make sure that everything is within the limits, because and if you go beyond the specified values of the manufacturer, and if there's a fault or damage to the equipment, then the insurance company will say, well, you operated it beyond the operation conditions, so I'm not going to pay for it. Anyway, so if you look for that here, so again we have the, you know, the limits here. Again, this is a different curve, so I'm not getting into like really detail, but you have the rotor heating on that region, that is the stability region, and I think there's also some excitation region is here. Okay, so this is the EF magnitude, I think, and so what you are end up is you need to, you know, operate so that region, so this is the operating region. So again, I'm not getting into the details, but you need to make sure that, you know, with all rotor heating, stator heating, saturation, prime mover, or the mechanical power limits, you know, that kind of limits defines your operating range. Okay, cool. So let's finish here, and in the next week I will solve a numeric example as well. Okay, thank you.